Good evening, everyone. I welcome you to this talk series CS Katha Barta, where we invite academics and professionals to deliver their talks. Our guest for today's talk is Dr. Ashutosh Modi. Dr. Modi is an assistant professor at IIT Kanpur. Before joining IIT Kanpur, he worked at Disney Research Los Angeles and Zurich. Dr. Modi obtained his PhD from Saarland University in Germany. He works in machine learning, NLP, and reinforcement learning. His current research interests lie in effective computing, legal NLP, text-based RL agents for common sense understanding, and NLP for sign languages. Dr. Modi's lab has been publishing at top international conferences and journals. He has been awarded Google Research India Faculty Award in the year 2022 in the Natural Language Understanding category. Today, he will be speaking on the topic titled Towards Natural Intelligence Technologies for Understanding Human Behavior and Activities. I welcome you, Dr. Modi. And
Yeah,
without further
thanks a lot.
ado,
Yeah, thanks a lot for inviting me, and thanks for the intro. I'm going to give a talk, which is sort of, I mean, at least the title is very different from what you hear nowadays, right? You hear people saying artificial intelligence, right? So I'm here talking about something different, which is like natural intelligence, which is the intelligence that humans should have and possibly have, right? So I'm going to talk about how I mean, okay, it's good to move towards artificial intelligence, but somehow the systems that we are developing or the technology that we are developing should also understand the end users of that technology, like in particular humans, how humans behave and what kind of activities influence their behavior. So what we are trying to do here is trying to develop technologies which is towards this line of research, where we try to understand human behavior and try to incorporate those things into the artificial agents that we are developing. So before I go into details of the talk, I will give a brief overview of things that we have been doing. So I basically run this exploration lab, the small logo that you see. Are you able to see my cursor as well? Is it
cursor I cannot see.
the pointer you cannot see? Okay.
No.
Okay, so at the bottom of the screen, you can see this. There's this exploration lab, right? So I run this lab in IITK. So there are like different areas that we work in this exploration lab. So there, I say that they're like different verticals. So like one of the first verticals and one of the core verticals is NLP and NLU. That's what my training has been during my PhD. So in this vertical, we work on legal NLP, trying to understand and process legal documents, and in particular the Indian legal documents. So India, as many of you might be knowing, has a huge backlog of pending cases, and we are trying to develop technologies which can sort of help to overcome this pendency by incorporating small techniques at different stages in the legal sort of pipeline. And also this involves like trying to understand the documents per se, and we are trying to develop like legal foundational models. Summarization is one another area, cross lingual reasoning, cross domain knowledge. So like legal, it's a huge domain, and they're like subdomains within legal domain. So how do you transfer knowledge from one subdomain to another domain? And then also like there's a one big project that we have recently started, which is on legal knowledge graphs. So other than the legal NLP, then there is another sub area that I'm working on is retrieving information from databases via natural language queries. So traditionally, if you want to retrieve information from a database, you would typically write an SQL query, right? So, but what happens sometimes, I mean, SQL, for writing a SQL query, you obviously need an expertise in writing a SQL and SQL language, and not everyone is expert in that. And moreover, if the query is, I mean, if you're looking for some information which might be nested or like doubly nested and those kind of things, then it becomes very tricky to write these queries. So, and this is obviously not a natural way for a human to communicate, right? So what we are trying to develop is some basically models which can basically translate a natural language query into a SQL query, and then can be used for retrieving the information from multiple databases. right? And then there is another line of research is which is dealing with biomedical text. So I mean, given that biomedical domain is kind of very varied and vast, there's huge amount of textual data in form of clinical reports and also other documents which is generated. So trying to extract information from these is a big challenge. So we are trying to develop some technologies there. And then one interesting uh, uh, area that I've started working on is something called machine learning. So all of you would have heard about machine learning. So this is something little different. So we are trying to unlearn few things that a machine has learned. So in particular, for example, you have LLMs which are trained on huge amount of internet text. So this so LLMs might pick up information which might be private to an individual, or which may not be I mean, let's say a person might have some objections about that information being there. So this here what we are trying to do is trying to explore techniques which can unlearn this information from the LLMs, right? So I mean, some of you might be knowing that there is also this right to forget information. I mean, the privacy law which is coming, it has this right to forget. So if someone, let's say some user wants certain information about them to be forgotten, so in these kind of techniques can be sort of useful. And then another direction is trying to understand like how LLMs align with the human ethics and etiquettes. So here we recently did some work where we try to assess how how the LLMs respond to etiquettes which are specific to certain regions. So as you might be knowing that etiquettes vary from country to country. Like the etiquettes which you have in, let's say, in India would not be there in the US, and in fact in US it might be considered kind of uh, I mean sort of anti etiquette sort of thing, basically, right? So what we are trying to assess is like, if you have a generic LLM, how well does it really understand etiquettes across regions? And our initial, we have a recent paper in EMNLP where we show that LLMs are really bad at this thing. And if you go from one region to another, they sort of kind of get confused and they tend to give wrong information. And this is particularly useful because, I mean, LLMs are being used in chatbots and all those kind of applications. So if you have, let's say, a chatbot deployed in some travel website, right? So it can sort of give wrong information to the traveler who's seeking some sort of information, and that can lead to a lot of problems because these are some sort of societal norms which anyone would not like to violate, if they, especially if they are going to some new country or some new region, right? And a little bit of work on automatic speech recognition, particularly in context of code mixed and code mixed Indian languages, basically. So this is one of the first verticals. And then the second vertical is trying to understand trying to understand human behavior and the decision making process that goes into this. uh, so in this, there are like three main sub areas that we are exploring. One is something called affective computing, where we try to understand human emotions and also try to develop some sort of generative models which can generate human emotions. And then there is the second line of research is trying to develop agents which can understand the real world and basically carry out certain activities in the real world, like common day activities which humans do even without thinking, basically, right? And this is sort of a step towards embodied AI. And then the third line of research is about in particular about mental health, right? And in so we are trying to we are collaborating with Nimhans, which is in Bangalore, trying to understand schizophrenia. So schizophrenia, there is a strong correlation between speech, language, and the schizophrenia condition. So people suffering from schizophrenia very often tend to have some sort of speech, some sort of thought disorder, and then that also gets reflected in their speech. So we are trying to understand these correlations and also trying to develop some sort of computational models for modeling this sort of phenomena. So I'm not going into details of these things because this is what I'm going to talk more in detail in the later part of the talk. And then the third and the final vertical is on the social good side. So India has around 66 million hard of hearing people, and they have really hard time communicating with the rest of the population. And if you look at the and these people usually use a sign language, in particular the Indian sign language, for communicating with rest with among themselves and with the rest of the population. But the interesting thing is that India only has 300 trained ISL. By ISL I mean Indian Sign Language interpreters. So you can see like the huge, I mean, the skew in the distribution, right? Like 66 million versus 300. So it's a big gap there. So what we are trying to develop is some sort of technologies which can aid the deaf community in communicating with the rest of the population. So we are looking at sign language translation system, generation systems, and also trying to understand the linguistic and the grammar of sign language. So sign language is not just about gestures; it's a very rich language on its own, and involves a very sort of rich grammar because it's sort of multimodal and like different the position of hands in space has different meanings, right? So that ways we are trying to understand that from more from the linguistic uh, perspective as well, and so that it could be incorporated into the deep learning models that we want to develop. So that's the
Yeah. Sorry. Yeah, I think there is a question. Aritra, you can unmute.
I want to ask what sort of data are you using for this sign language interpretation? Is it image data
No,
or
no, it's a video data. So what we do is it's a multimodal data. So we have video where the signer would be saying something, some sentence or something, and then so depending on the task, suppose if we have a translation task, so we'll have a video of a signer, and then the during training we'll also have the corresponding text of that particular video.
okay, okay. Thank you. So basically, it is sort of image data,
Sorry, sort of what?
sort of image data.
No, no, not same. It's a video, so it's frame by frame images sort of thing.
So are you using some sort of RNN?
No, we are actually using transformer based architecture, which also which
Okay.
are I mean which
Yes,
have
yes.
better performance than RNNs, right? So
Mm-hmm. Okay, okay. Thank you.
yeah, you can actually check out these papers as well. I mean, we are I mean these have more details about these architectures. All
Okay, thank you.
All right. So now I will move forward. So yeah. So for today, I'm going to talk about this particular vertical about understanding human behavior, and that's the natural intelligence part which comes in, right? So I'm going to start with the affective computing part first. I mean, first let me try to explain why should we really care about affect or emotion. And usually, I mean, if you look traditionally, people have sort of thought that emotions and rational thinking are sort of orthogonal to each other, right? But there has been a lot of studies in past decade or so where I mean, especially in the neuroscience community, where they have shown that emotions or affects are important or integral part of our rational thinking. And whenever the part which deals with emotion is sort of maybe damaged due to some accident or something happens, even the rational behavior gets affected because of that. So that is sort of a very so that means that it's sort of an integral part of human behavior, and it is that makes it really important to understand what's going on there, and because then this can be incorporated into the algorithms that we develop for humans. And also to give a more sort of a concrete and a practical example, so all of us have these personal digital assistants nowadays, right? I mean, like Alexa, Siri, and all those. And this is like one of the interactions which I had with the with my personal digital assistant one of the days. So I didn't have a really good day. It was a long day, so I just came back home, and then as usual, the assistant sort of just greeted me with hey, and then hey buddy, and then as usual it asked me how are you doing, and then I said in a very low tone and sort of I mean the pitch was also sort of low and intonation was not there, and I had a long day, but it completely missed all those cues, and it took it something different, and it just say let's celebrate, and this was sort of like pissed off me even more, right? So the thing to note here is that currently the machines fail to understand the emotions that humans have, and these emotions play an integral part in the communication that we have at person to person level, right? Sometimes you may not be even speaking anything, but even your facial expressions might be enough to convey a lot of things that you want to that you are not speaking, right? Certain emotions that you are not speaking, or you're not basically explaining in detail, basically, right? So if the machines could sort of capture these kind of emotions or affects, then they can they can generate appropriate response, and then they can also help us in sort of decision making process. And the study on emotions has a long history, actually. And they have been there was this guy called Paul Ekman, who showed long time back that there are certain emotions which are universal across all cultures, basically, right? All societies and cultures. And so humans tend to express certain emotions almost in the same way across these different cultures. And emotions, so if you want to develop machines or systems that interact seamlessly they with humans, they need to understand the underlying emotion of the person they are interacting with. And so emotions are not just about the surface level information, but they are actually also conveying the underlying thought process, and they are important part of communication. So Marvin Minsky, which all of you would be knowing, that is one of the founders of AI, the field of AI, right? So he has written this really nice book called Emotion Machine, and in which he has written this very nice line that emotion is not is not specially different from the processes that we call thinking. So he very clearly says that emotions are an integral part of the thinking process. So if you want to really understand what the person is thinking, you also need to understand what emotional state or what emotional profile of that person is. Right. So this sort of motivates why we should actually be concentrating on understanding emotions. And to speak more formally, so the field of affective computing is about studying and developing systems that recognize, interpret, process, and simulate human feelings and emotions. And so this the field of affective computing was proposed by Professor Picard. She's at MIT, and she's still quite active in this area of research. And this is also popularly known as artificial emotion intelligence or emotional AI. Right. So, and this has a lot of applications, and I here show just like some of them. Like this can be very useful for understanding customer behavior in like call centers and customer calls, basically, right? And then similarly, this could be useful for analyzing social media text. I mean, social media is so prevalent nowadays. I mean, a lot of people say a lot of things about different products and different things on social media. So understanding the sentiment and the emotion of those let's say tweets or Facebook posts can help a lot to can be helpful for some companies, for example, right? And another interesting technology, another interesting application could be in the vehicles. So for example, in vehicle the if the let's say you have a car which is smart enough to recognize your emotional state, so it could help in preventing certain accidents. For example, if you are not really in a perfect state of driving, then it can detect those and then sort of prevent you from driving in such conditions and help prevent any mishap from happening. And also so it can be useful for understanding the audience. So you have, let's say, an audience which is watching some movie or some series, and then if you could see the emotional profile of the people when they are watching the movie, then that could help you to understand that what content is liked by the audience and what is not liked by the audience, right? So, and that can help you to improve your content further in the future. Right. So yeah, so that's about the applications, and these are, as I said, these are not exhaustive list. There are lots of other applications. So so now I hope you are all convinced that we should be developing machines which understand human emotions. And so if so more at the fundamental level, if you want to develop such machines, there are two class of problems that need to be addressed. So one is the first class of problem is has to deal with the recognizing and predicting the emotion of a person. So let's say if you have a sort of a personal digital assistant which also has suppose that has a camera, then it should be able to recognize what emotional state you are in, and or predict what emotional state you are in based on the facial features, your body language, your voice, and what your the content of your whatever you are speaking, and based on all those features. And similarly, so that's the first class of problem. And once you have, let's say, been able to predict or recognize emotions, then the other class of problem that you need to address is, emotion generation, right? So you don't want the machines to be passive, right? So the interaction between machine and humans is quite dynamic and active. And if the machine is just saying things in a very plain monotonous voice, then obviously the person would lose interest pretty soon. So the machine should be exhibiting similar emotions as humans, so that the interaction is sort of seamless. So that's the second class of problems that need to be sort of addressed. Yeah, you have a.
Exactly.
Yeah, Dr. Modi, so one quick question. Does this go through the same thing as like automated vehicles do? Like, as in the moment you do this emotional, let's say, interaction,
Mm.
like there is nothing to be accountable, right? You cannot account humans anymore when you are dealing with, let's say, any psychological stuff, right? Let's say depression or just talking, and then it goes very bad. You cannot blame the computers there. Similarly, like for accidents, you cannot blame computers. So does it go to, do we think about that in this or no?
No, okay. I actually didn't fully understand the question. So you're saying, like, in particular, like in context of, let's say, vehicle, if let's say you have a system which is monitoring the emotion of, let's say, a
Oh no,
person.
so I'm saying like if there is an autonomous vehicle, let's say, and it gets into accident, you just cannot blame the vehicle to be the problem. So similarly, I'm saying if emotion generation and prediction and recognition is there, it's a very human interaction subject. So if machine does wrong generation of emotions or wrong prediction of emotions or wrong recognition, then who is to be blamed? Like, given
Oh,
you can,
that's actually a very interesting and sort of an ethical question, right?
I'm saying like, do we look at this when we
No,
write
not
papers?
exactly at that front. So this actually goes also into legal matters, right? Because
Yes.
it has to be sort of well defined who would be responsible. See, you can even go further, right? Is it the, I mean, you can also blame the developer or the engineer who developed the system, right?
Correct, correct.
So yeah, this is sort of yeah, I don't have a clear cut answer for this thing, and
Acha.
I think it needs much more discussion. And it's not just the emotion thing, but the kind of things. I mean, the kind of decision you come for this kind of problem would be applicable for other settings also, similar to like automated vehicles and all those things, right?
True, true.
Uh,
It's
I,
a more broader area, I would say. So we are not currently exploring that.
I
Okay.
also have an additional question maybe here,
Hmm.
because here the effect of I mean, how much is the damage that is caused by this
Hmm.
ethical issue would also matter, right?
Yeah.
Uh, I mean, like unlike in the case of automated vehicle, let's say,
Mhm.
it could be harming the life, but here it might not be in
So here
some
also
case.
it could, right? It could possibly. So suppose you
Uh-huh.
have, I will give you one use case. So suppose, see what happens. Suppose let's consider this a hypothetical use case. You have a, let's say, a Air Force pilot, right? Who and he's driving a, let's say he's flying a plane which has this kind of system which monitors the stress level and the emotional state of the pilot. Suppose the system goes wrong, then it can be sort of a I mean, some sort of a really bad. I mean, it can give wrong suggestions to the pilot, and it can lead to a lot of problems, right? It can be lethal. Right?
But still, there is a human who is responsible for taking the. I mean,
Ah,
the machine
yeah,
can suggest, but the
machine can
decision
suggest,
would
but
be.
yeah, machine can suggest, but sometimes if see, there's also this tendency among humans to blindly believe the machines, right? And
Right.
you might have also seen that people tend to believe other people less compared to machines, right?
Mm.
That's sort of a more psychological thing that happens with very often with people who are not technologists per se, right? People who are sort of the end user of technology, who have never developed technology on their own, they tend to believe technology more very often compared to other humans, right?
True.
So
True.
so that's why it can be sometimes. I mean, it depends on the use case, as you said. But sometimes it depends on if you are putting this thing in some very critical application, then it can be sort of lethal.
Yeah. Okay. Thank you.
All right. So now, see, what we want to do is, so emotion is not just, it's not an isolated phenomena, right? It is involving a lot of different modalities, like your facial expressions are involved, eye movement is involved, your voice is involved. And even going further, if you look at the physiological parameters, right, like your pulse rate would be changing for certain emotions, and all those things would be there. So what we want to do is, we don't want to predict, let's say now I'm talking about the emotion prediction part. So we don't want to predict things in isolation. So what we want is, we want to take information from all the different modalities and then sort of take them together. So in fact, different modalities might complement each other with regard to the affect information. So that's the multimodal part of the affective computing. And the other part is like, okay, you have information coming from different sources or different modalities. How do you fuse them together? So people have come up with different sort of fusion techniques. Like you might have early fusion, where you try to fuse the information at the early stages itself. Then there is something called late fusion, where you process the information from each of the modalities and you try to fuse the output of corresponding to different modalities at later stages. So there's no clear cut answer to that. And this is an active area of research, how the fusing different sources of information. And then the other part is that emotion or the affect does not, it is also affected by the things that are in the context, right? So if, let's say, two people are talking to each other, so it is going to be affected by the things they have spoken in the past. Or maybe, let's say, if I start talking with you, maybe let's say 2 or 3 minutes later, my emotion might get affected by what you just said before, right? So that context is really important. And also context in terms of like the surroundings and all those things can also play a role. So the affect prediction has to be contextualized. So what we are aiming at is multimodal contextualized affective prediction. So that's what we are sort of looking at, if you really want to predict emotions or affect in more holistic way, right? So that's the sort of the general line of research that we are looking at. Now I'm going to talk about some particular papers related to this line of research that we have in the recent past. So starting with the first one, which is called Cogmen, contextualized GNN. So GNN is graph neural network, GNN based multimodal emotion recognition, right? So contextualized and multimodal part I already sort of explained in the previous slide. And GNN is sort of some sort of specialized graph neural network architecture, which I'm going to talk about in a bit, right? So what's the problem setting? So the problem setting is called emotion recognition in conversation. So here you have, let's say, some people, let's say two speakers who are talking to each other, and you have this conversation going on. And what you want to do is, so okay, so this conversation, as you can see on your left, you have these speaker one and speaker two. So there is this dialogue between these, and then each thing that one speaker says is called one utterance. So you can see U1 on the leftmost side, and then on the middle or the maybe the right side, you have U2, right? So this is the first utterance spoken by the first speaker. Similarly, U2 is the second utterance spoken by the second speaker, U3, U4, and so on and so forth. So what we want to do is, given this conversation going on between, let's say, speakers, in this case it's two, you want to predict the emotion of each and every utterance. What's the emotional state of the speaker in each and every utterance, right? So, and so this conversation is in form of it's multimodal. So you have the video of the conversation. So here the video would have obviously the body and the facial features and everything, and then audio is going to be there, and there is also a transcript of the audio available. And you want to make use of this. So we have three modalities, like text, audio, and visual. So what you want to do is, you want to make use of these modalities and information to predict the emotion of every utterance, right? So is the problem setting clear?
Yeah.
So yeah, now let's now I'm going to talk about the model that we developed for solving this task, the emotion recognition conversation. Before I go to the model, I will talk about the intuition behind the model. So there are two sort of sources of information that we want to capture here. So the one is the the information which is at the global level. So this is basically going to capture the underlying context of the emotional state of a speaker throughout the throughout the dialogue. So it's sort of I mean, in a, roughly speaking, it's sort of capturing the underlying mood of the entire conversation, right? And then there is the other source of information, which is the local information. So if, let's say, if I say something now, it's going to affect you in the next utterance that you're going to speak, and I'm also going to get affected by myself. What I just said, let's say, one utterance before, is going to affect me now at this utterance, right? So that sort of inter and intra speaker dependence is something what we want to sort of capture, right? So these are the two sources of information that we try to model. And now let's look at the Cogman model, Cogman architecture. So at the input to the model, as I said earlier, is a video. So video has text in form of the transcript, audio, of course, and then the video information. So what we do is the video is split into frames, where, or maybe small snippets, where each snippet is capturing one utterance, right? You saw in the previous slide that there is different utterances, right? So you capture each of, though you split the video into utterances, and for each utterance, so here you can see at the bottom you have this u1, right? U1 superscript a, u1 superscript t, u1 superscript v, right? So these utterances, so this is u1 is the utterance, and then you extract the audio, which is a text, and text, t is the text, and v is the video features from this small snippet. So these features you extract, and you do it for all the utterances. So, like, for example, text features could be output of, let's say, a BERT model, right? You pass the transcript to BERT, and then you get the text feature. Similarly, audio features could be features you extract using some sort of open smile kind of features. And video features could be like body pose, and then facial features, and those kind of things. So you extract these features, and you extract these features for all the utterances in the dialogue. So let's say you have n utterances, so you have u1 to un. So you extract these utterances, and then you process, you pass these utterances through a encoder, which is a transformer in our case. So, and this transformer will give a representation of each of the utterances. So here you can see z1 on the top, and z2 and till zn. So these are the representation in form of a vector for each of the utterances. So transformer takes in the features from the video and gives out the representation of each utterance in form of a vector of real values. So once you have this features, or the representation of each of the utterances, what you do is you form a graph structure. So in this graph, you have nodes and edges. So each node is corresponding to one utterance, right? And edges are capturing certain kinds of relationship between different utterances. If you remember, I said there are two sources of information. One is the local and one is the global. So we are trying to capture that of kind of information via these edges, right? So they're like, if you look different kinds of edges or different kind of relations, so they are like relation between with the past utterance, relation with the future utterance, intra relation, which is what I say now is going to affect my utterance in let's say in the future, and then inter, what you say to me is going to affect my utterance, right? So that sort of inter and intra kind of relations. So we monitor these relations in the graph in form of edges. So they are like different types, essentially four different types of edges, and each edge has certain weight associated with, and each node also has a feature vector associated, and these feature vectors you are getting from the transformer encoder. So now you have this graph where there's a representation of each node, and there is a representation or a feature vector associated with each edge. And what we do is we learn these features of the edges and the nodes, so via something called a relational graph convolution network. So I'm not going to go into too much details in the interest of time, but this graph convolution networks does something called some sort of message passing and tries to capture the information from the nodes. Let's say I want to learn some sort of representation of a node. I'll take in information from all the nodes which are connected to me and try to collate that and try to come up with some sort of representation. And you do this at multiple layers, basically, right? So that gives you some sort of representation for each of the edge as well as the each of the node. Once you have that, then you basically apply, graph transformer on top of this, on these edges and nodes, and then you get these representations which you can see on the top as h1, h2, hn. So once you have these representations, and then you can apply some sort of a linear classifier over these representation to predict the emotion of each and every utterance, right? So you have n utterances, so you get these n outputs, right? So that's the model, the entire emotion prediction model.
I have a question here. So here in the second step, the graph formation, how are these edges determined? These
Yeah, so see, so basically what you do is, uh, you connect all the edges. Okay, so you basically, uh, you have these four kind of relations, right? So based on these relations, like let's say my utterance is going to affect my future utterance, right? So
hmm.
that kind of edge you connect, and then your utterance is going to affect me, so then again that edge you connect. So based on
So
these, in the dialogue you connect these basically.
okay, okay.
And then the weights of these edges you learn via the relational
Yeah.
graph.
So it is not based on the ZI values. I mean the connections between the nodes is not based on the
So
vectors represented ZI, let's say.
so the weights of the edges are going to be affected by these, right?
Yeah, yeah, yeah. No, no. I'm saying the connections,
And the
not
connection.
even the connect vectors corresponding to the edges, just the edges. I mean,
So you're saying the z, yeah, the value of the z, the vector, is not going to
affect whether two
connect or not.
ZIs will have a connection or no.
Yeah, yeah. So connection is based on the dialogue, actually,
Okay.
the structure of the dialogue.
So that should come from the data set itself, right?
Yes, yes.
Okay. Okay. Thank you.
All right, so this is the entire architecture. So, and this is the main model. And then what we do is, once we have this model, we sort of test it on different data sets. So there are two main multimodal emotion recognition data sets which are out there. One is the IEMO cap. So these are like didactic conversations where two people are talking to each other, and there is a video of people talking to each other. And then there is CMU Mosaic, where these are there is a speaker who is speaking about something. I think these comes from YouTube, where there's a speaker, they're talking about certain topics on YouTube. And these data sets are sort of the standard data sets that are used for emotion recognition, and these are annotated with different emotion labels. So and these are the different so this is for the IEMO cap dataset. So as you can see, there are like 6 emotion labels: happy, sad, neutral, angry, excited, and frustrated. So these are the emotion categories that are there. And here you can see, like, we are comparing with different models. So the last row in this table is the Cogman architecture, and the others are different models that are there, which have been proposed in the past. And we can see that overall the model common architecture works pretty well compared to the previous. For certain categories it does not perform as good as the previous work, but overall it's pretty good, right? And then if you look at the performance of overall performance of the Cogman architecture, it is like one of the best. And this is a snippet from the Papers with Code website. So Papers with Code website tracks different tasks, maintains leaderboards for different tasks and different data sets that are there, not just emotion, but in general for all the NLP tasks and all the data sets that are there. So in particular for multimodal emotion recognition, Cogman seems to be having the best performance as of now. And this is on the other data set, the mosaic data set that I just said. And here also, I mean, Cogment in general, I mean, overall performs much better than the previous work, right? And then we also compared with so we have like three modalities. We can also do one thing is we just don't take the audio and the video modality, but just take the text modality. So we also compare with the unimodal approaches, which were just based on text. So there also it has a much better performance. And similarly, and okay, so people also do 4-way and 6-way classification, where they take only four emotion categories. They merge few categories and they just take four categories, and then there is the 6-way categories. So in both, it seems Cogment seems to having competitive performance, right? And then we did some sort of ablation study, since our model has different components, right? So what happens if we remove the graph neural network? Without that, so we see that without the graph neural network, there is a dip in performance. And if we make all the relations same, like we were distinguishing between different types of edges, if we remove that and make all the edges same, then also there is a drop in performance. So this clearly shows that we are trying to capture different sources of information via different types of edges, right? And then also so how many utterances you take. So in the model, you see we had u1 to un, right? So if instead of those, if you instead of taking all the utterances, if you just took, let's say, 10 utterances, and then you did the prediction, so there is a sort of a drop in performance. If you take lesser utterances, there's even further drop in performance. So there is information which is being shared across all the utterances. So that, I mean, so essentially what it means is that the context is really important. So you have to take all the context into account for prediction, right? And then we also did some sort of analysis of the features that are coming from the GNN. So before the GNN, the features were sort of kind of mixed, as you can see here. And then after the GNN, there is some sort of clustering which is happening, which helps in basically making good predictions. So if you want to know more, I didn't go into too much details of the paper in the interest of time. If you want to know more, the entire code is available, and all the I mean data set and everything is there. So if you want to experiment with this, please check out our code repository. You can download the code and everything and play with the code, and also try to apply this model to other data sets as well. All right, so I hope everyone has sort of noted down the link. And yeah, so then there's another line of, or maybe another related research that we have done, which is also to do with emotion recognition conversations. The problem setting is similar to what we saw earlier, but here we try to make use of another intuition to predict the emotion. So the intuition comes from someone called Kurt Vonnegut. So he's very famous for something called shapes of stories. So what he proposed is that every story, a long time back, he proposed that every story has a shape which is plotted by the ups and downs experienced by the character in the story, right? So, and this also sort of defines the emotional arc of a story. So for example, you see here on your left is Ramayana, right? So Ram is undergoing certain different types of emotions in the story, right? So there is this kind of emotional arc for the character Ram. Similarly, in Mahabharata, there are different characters who undergo different sort of emotional state as the story progresses. So there is different kind of emotional arc. So what we propose is that can we capture this emotional arc in conversation? So every speaker in the conversation is going through some sort of emotional ups and downs, or some sort of emotional arc, basically. So we want to capture that information, and this is we do this via this model. The model looks a bit complicated, but it's not that complicated. So the idea here is that we have some sort of a GRU for every speaker. Here you can see speaker A and speaker B, and we also try to capture the change in emotion, or the likelihood of change in emotion of a speaker when they move from one, let's say, one utterance to another utterance, right? And this is done by the network that you see at the bottom of the slide. This is some sort of a Siamese network which takes the embedding of the, or maybe the embedding of the thing that the speaker has spoken in the past and the current, and then tries to predict whether there should be a shift in emotion or not. and if there is a shift, then it should guide the current emotion of the speaker. So the shift is basically used to guide a GRU. We have a modified GRU architecture here, and the output of GRU is a emotion label basically, right, which is predicted, as you can see on the top. And so that's the sort of the intuition. We want to take into account the context as well as the likelihood of change in emotion based on the emotional arc of the story. So yeah, here again, in the interest of time, I've skipped a lot of details. If you want to check out the paper and the code that is also available, you can find it at this repo basically. Right. So yeah. So now I'm going to wrap up this part of the talk. So going in forward, what we are trying to explore is, so even within emotions, so you have these different categories of emotions, but there's some sort of hierarchy which is there in these emotions. So as you can see on the figure on the right, there is some sort of a dendrogram on the top, right? So this dendrogram is actually capturing some sort of hierarchy in the emotions. So there's some sort of taxonomy which is there in the emotions, and there has been research which has shown about this taxonomy. So the idea is, can we develop models which capture this taxonomy, and can we develop something called emotion embeddings, which are actually developed by applying some sort of hyperbolic, which are learned by via some sort of hyperbolic neural networks applied to these applied using this taxonomy basically. Right. And then another interesting line of research that we are exploring is like trying to understand the cause of emotion. So if there is an emotion that is being expressed by an individual, then obviously it would have some sort of cause. So the idea here is that, can we find out the cause? Let's say you have a conversation. If let's say in some, let's say 10th or 10th, there is an emotion expressed by a individual, what was the possible cause of this emotion from the previous utterances? So that's kind of the thing that we are looking at. And then also emotion has a very strong correlation with the decision making process. So if someone is in really bad emotion, they, or maybe let's say they are angry, the kind of decision they will make is going to be very different from if they are happy, right? So that sort of things we are trying to explore. This also sort of involves some sort of neuroscience part. And then in particular, we are looking, so the data sets that we saw were very west centric, and they have been built from the western basically the people who are involved in that are from the western societies. But we also want to understand how do these things work in the Indian setting. So we are trying to develop multimodal data for the Indian setting. Basically, you can have, let's say, videos where people are talking to each other, particularly in Indian settings. So this can involve not just English but also other languages. So it can be multilingual sort of thing. And then obviously, as I said earlier, we are also trying to understand how does the emotion play a role in the mental health. So for example, if a person is suffering from some sort of depression or anxiety, then their emotional profile is going to be very different from a normal individual, right? So these are the different directions that we are planning to explore. And then now I'm going to move to the next part of my talk, which is about developing these agents which can be deployed in the real world. So this is one of our recent work, which is called Script World, text-based environment for learning procedural knowledge. So the idea here is that, I mean, the research question that we are asking here is that, can an agent learn to do daily chores as effortlessly as human without any explicit supervision? So for example, you want to, I mean, what if you can have a robot which can plant a tree without you actually guiding it to uh, guiding each and every step that is required in planting a tree, right? And as you know, that humans have this implicit common sense knowledge about the world, and they can do these things very effortlessly, right? So now the more fundamental question is, what is the nature of this knowledge, and how do you actually impart this knowledge into agents? So for the first part of this question, the nature of this knowledge, so this takes us sometime back into the past, where a researcher called Roger Schank tried to answer this question via something called scripts. So he defined scripts as sequences of actions describing stereotypical human activities. For example, like cooking pasta, making coffee, so on and so forth. So here you can see the sequences of steps or sequences of actions that are involved in washing dishes. On your right, you can see you take dirty dishes, run water, add soap, and so on and so forth. So these are the sequence of actions or the events that are involved in washing dishes. And so this sequence of actions or events we call as event sequence description, or ESD for short. Right. So if you analyze this script knowledge, right, so it is sort of a highly non-linear structure, and there are multiple ways of doing the same activity, and there are alternate ways of doing the same activity. So there's some sort of different if you look at the graph structure of a script, they can be alternate paths, and then sometimes the order of the events can also be changed, something you can do earlier, and or you can flip the order of the events, right? So sometimes you can preheat the oven earlier and then start mixing the ingredients, or you could do the other way around as well, right? So the script knowledge is non-linear and is kind of challenging to sort of capture and model, right? So as I said, there are multiple ways of describing or doing an activity, and this, if suppose if I asked people to write how would they wash dishes, so they will come up with different ways. Here you can see four or five different ways of doing the same activity. So there is sort of a lot of variation involved in doing the activity, both at the lexical level and also at the conceptual level, or at the action level, basically, right? So this actually can be useful for us, and this is what we did. We create so there is a corpus called Descript corpus, where they asked it's a crowdsourced corpus, so they asked the people to describe activities in form of different actions and different steps they would take to achieve the activity. And they did this for 40 scenarios. So here you can see 10 scenarios from those, like taking a bath. So they will ask people how would they take a bath, so they have to write step by step, sort of in a telegramic style, uh, of doing this activity. Like, for example, how would they bake a cake, right? So they will have to write these steps. So and each of these activity we call a scenario. So for each scenario we ask 100 people, and these 100 people come up with 100 ESDs. As I told earlier, each sequence of actions is, or sequence of events, are called ESD. So these 100 we are given these 100 ESDs for each scenario. So what we do is, in fact, not exactly we didn't do this, but the authors of this paper, Descript, whom I know pretty well. So what they did was they semantically clustered. So what they did, they clustered the semantically similar events in each of these ESD for 10 scenarios. So these 10 scenarios that you see on your right, for each of these, they took the events which are similar for each of the scenario, and they clustered them together. And this sort of gives us some sort of a clustering of the similar events. And this will become clear in next few slides why I'm talking about this thing. So this also introduces the script world environment. So this is a text-based environment, which is for useful for teaching common sense knowledge, or in particular script knowledge about the world, to the agents in an unsupervised way. So, and there are different design choices which are involved in script world, like the complexity of the environment should be, environment should be obviously complex enough, and there should be enough flexibility in the environment, like different choices, different sort of variants of the environment should be there. And of course, it should be grounded in the real world, right? And so in order to solve the script world environment, the task requires the agent to maintain some sort of memory and take complex sequential decisions in this environment. And one thing to note is this environment is dynamic. Every time the agent is playing or is deployed into this environment, it will see a different version of the environment, right? And this is sort of step towards embodied AI, where we want to develop agents which could be, let's say, deployed in metaverse, or one of those virtual settings, basically. Right. So yeah, I think so a few things may not have been clear till now, but this environment creation process would make things clear. So as I said, for every scenario, you have ESDs. So here you can see like 4 different ESDs for buying a medicine scenario, right? So what you do is, first, the things which are semantically similar are clustered. So here you can see that search for medical store, look for nearest store, locate medical store. These are semantically same thing. They are essentially meaning the same thing. So they are clustered together. So you form these different clusters, and then you form a graph based on the ordering of the events or the actions that are there in the original ESDs. So this graph actually is the script world environment, right? So the and these edges are the order in which these activities or the actions would be taken, right? And so so this is your environment. So what we do is there's an agent which will be deployed in this environment, and the agent is going to implicitly following this graph structure. Obviously agent doesn't know the underlying graph, and it has to figure out this graph. It has to learn this graph on its own, basically, right? So so this let's say it is at the start node. It will start with this graph, and the environment is going to give certain observations based on the node. So each node is a state. It will get certain observation, and based on these observation it's going to take certain action, and based on these action it's going to get into another state or another node. Suppose it takes a, let's say it's in this green node, it takes a wrong action, it might be teleported back to some previous node or previous state. If it takes a right action, it would go to this purple node, which is forward towards the final code, which is the end node, right? So this is how it will basically traverse through this environment, and for every action it is going to get certain rewards, and based on these rewards it is going to learn what is a good action and what is a bad action, right? So we develop script world for these 10 different scenarios, and the underlying graph structure is much more, it's highly complicated. I mean, it might look simple, but as you can see, the number of paths is huge. Actually, it's I mean, like for example here 3 into 10 to power 27, that's a huge number of paths that are there for taking a path scenarios, right? So once you have this graph, and then so this is how the environment looks like. As I said, this is a text based environment. So here you can see in the beginning, the agent is given the main goal that it has to do. So for example, going grocery shopping is the main goal here. So at every step, the agent will be shown different choices. Here you can see 5 choices, and these 5 choices are the actions. So the agent has to select the correct choice or the correct action, and based on what it want to achieve in the end, and based on the action, it will get certain rewards, right? So for example, it might get a positive reward or a negative reward based on the correct action or incorrect action, right? And then it also gets 5 chances, so it gets 4 lives essentially. If it gives 4 incorrect answers, so the game is over basically. So the agent is basically loses. But if it gives the correct answer and leads is basically arriving at the final state, which is the goal state, then it gets a 10 points basically. So the 10 is the maximum point that it can get, and for incorrect action it will get a 0 point reward, right? And so all these numbers are sort of flexible, we can change around. So that's the sort of flexibility in the environment. In fact, the number of choices that you see, we can also change. In certain versions of the environment, we can have only 2 choices, we can have 4 choices, 5 choices. So that's kind of up to us. Obviously, if you have more choices, the game becomes more difficult and obviously more interesting, right? So so any questions so far on this environment?
Not yet, it seems. Yeah.
Uh-huh. Okay, so I hope, yeah. So I'm going a little fast, but I will share the link of the paper and the code so you can explore more in detail. So once you have this environment, right, and then the agent is playing this environment, and now let's look at what kind of agents we experimented with. So we experimented with some of the standard baseline RL agents like DQN, actor critic, PPO, recurrent PPO. So the idea here is that agent has to learn the queue function and the policy. So policy is basically a distribution which tells what action to take when you are in a particular state, right? So this is sort of the standard RL policy terminology. And so we have these agents. So there's a question.
Oh, yes. Let me read it out. Are the list of actions generated automatically by the model, or does it follow some pre-built graph or set of possible paths?
So the list of actions, yeah, that's a good question. So list of action are actually coming from a underlying graph structure, right? But the verbalization of the action is actually sort of automatic. We actually used some sort of a language model to come up with different variations of the same action, right? So for example, you might have the turn the car on, but there could be other variations or different paraphrases of the same action, which we get from the language model. Is this clear?
Yes, yes, he says.
Okay. So then, so see, if you look more deeply, script world is actually a POMDP, partially observable markov decision process, and we are trying to solve this environment. I mean, basically, we are trying to learn these either Q function or a policy, right? So if we started from scratch, right, it will be very difficult for an agent to learn because agent has no knowledge about the real world. So what we try to do is we try to club the agent with a language model. Like in our case, it's a SBOT language model, which provides some sort of prior knowledge about the real world. And this is integrated with the RL algorithm. So the environment is providing the observations in form of actions to the agent, and these actions or the observations are converted into a vector using a language model, which sort of captures the knowledge about the real world, right? And then these are fed into the RL algorithm. And as I said, okay, and then as I just said, like these generate the embeddings, and these are used in the RL algorithm. And in fact, they are concatenated with the input into the learning framework, right? And so these are the results of different agents. So as I said, like there are two versions of the environment. One is where we provide some hint to the agent, as you saw in the previous slide that there was a hint, and there is another version where there is no hint provided. So what we observed is that for the agent, when a hint is provided, it is almost able to solve the environment pretty well. So as you remember, the maximum score that an agent can get is 10. So here you can see for different agents, it's almost very close to 10. But the interesting setting is where you don't provide a hint to the agent. So the hint, when there is no hint provided to the agent is sort of, in all the cases, all sorts of agents are struggling to sort of solve the environment. In fact, for some of them, it's sort of negative score. And what we observed is the recurrent PPO agent is performing the best, basically. So, and these are the scores over different number of episodes, as you can see, and for different scenarios. As I said, there are 10 scenarios. And in this case, there are two choices and there is no hint provided. So as you can see, initially, obviously, the agent is struggling, but slowly starts learning what's the correct sequence of actions, and towards the end of the I mean, towards the later episodes, is almost able to solve the environment, right? And then this is across different agents, like how is the performance. And as I said, like RPPO is performing the best. DQ and to some extent A2C is not performing that well, right? And then so we also experimented with, like as I said, there was SBOT model that we tried, but there are other language models also that can be tried out. So we tried out other language models as well, and we also tried simple non-contextualized embeddings, like glove embeddings. So as you can see, when you use glove non-contextualized embeddings like glove, the performance degrades quite a bit. So that means the context is really important. So that's why the language model helps a lot. Right. And then we also try to see the generalization performance. So what we do is we train an agent on one scenario and try to see the performance on another scenario. So here you can see, let's say an agent is trained on bus. It also tends to perform slightly well on the train scenario, right? Because bus and train have some sort of similarities, right? But what was interesting to see was that, let's say agent was trained on airplane, it is able to perform slightly better on library, because there might be certain things which might be common. For example, library, you might want to check out certain books, and in airplane you might want to check out your luggage and those kind of things. So some activities might be common, so those things happen. So this is for with handicap, where you provide a hint. When you don't provide the hint, the generalization gets affected, as you can see in this. I mean, there is very less generalization, right? So this is sort of an active area of research. How do we develop agents that generalize across scenarios, right? And similarly, so this one was with two choices. If you go to five choices, obviously the setting becomes much more difficult, and generalization is almost not happening there, right? And then so you can also have different choices. Number of choices can also vary. It's like 2, 4, 3, 4, 5. So based on these, but what is interesting is, for no matter what number of choices you have, the curves are kind of similar. So there is a dip, as you can see, and then it starts increasing. So this is sort of an interesting phenomena. And so going a bit more into this phenomena, what happens is, here I'm plotting the scores of the agent along with the number of the cumulative node coverage, how many nodes it has covered basically so far. So what we observe is something really interesting. There's some sort of exploration, exploitation trade-off which is happening. So initially, the agent, what it tries to do is, it will try to explore as much as possible at the expense of getting negative reward. So this, but it makes sure that it doesn't die while doing so. So it will, let's say, let's say it has 4 lives, what it will do is, it will do 3 incorrect actions and just do the fourth action correct, so that it doesn't die, but still it is able to explore. So as you can see in the initial episode, it is exploring, so the score is going down and the node coverage is slowly increasing. But once it has explored enough number of nodes, it has a fairly good idea about the environment, and it starts now exploiting the nodes it knows well. So then the score starts increasing, right? So till almost 80%, the score is 80% node coverage, the score is decreasing, and after that it starts increasing because it knows enough about the environment. So this is sort of an interesting exploration exploitation trade-off which is happening there, right? So to yeah.
Yeah, so a question here. How is the feedback from world to the agent is given? Language model or human annotation?
No, it's in form of a reward. It's a score actually. It's a scalar score, plus like -1, +1, 10, -10, a scalar score, like you do in a standard RL setting.
Right. So,
Is it
okay,
possible?
I think we can go ahead. Maybe it was there in the chat. So, yeah.
Hmm. All right. So now, just to summarize, I mean, we have developed this script world environment. It's just like the initial step where we want to teach procedural knowledge to agent, and we used language model to provide some sort of prior knowledge about the world, right? And right now, we saw the agent was getting certain choices in form of action. So the interesting thing is going to be, if the agent could directly say the action in form of language, and then the environment sort of parses that action and says whether the action is correct, or gives the reward based on the if the action is correct or not, right? So that's another area that we would like to explore further. So if you're interested in the code and the environment, everything is available on this repository, so you can read more details about the environment and the agent in this paper, in the paper as well, which is also there on the repository. So just to conclude, so in the future, what we would like to do is develop some sort of multimodal environment. What the environment that we developed was sort of very textual. So what we want is that the agent is in some sort of a visual. There's also visual modality involved. An agent has to do certain activities based on the visual modality as well as the procedural knowledge about the world, right? So more on the agent side, there can be some sort of hierarchical learning in the agent. So the scenario can be divided into sub scenarios or sub goals, and there might be certain agents which might be accomplishing the sub goals, and then there might be a master agent which would be coordinating among these smaller agents, and then some sort of self learning in the agents as well, right? So the agent should be able to sort of learn some sort of generalized representation of the nodes which are there in the underlying graph, and then sort of would help it to sort of solve the task in a better way. All right, so I think I would conclude there. So yeah, I talked about like different. I mean, as I said, like we are exploring like different verticals, and in this talk, I talked in particular about the second vertical that you see in the middle, right? And I covered the affective computing part, and then the embodied AI part. So yeah, and if you want more details, I mean, you can the papers and publications are available on this QR code link, so you can check out there. and also a little bit of self promotion. So in case anyone is interested on working on these interesting problems or other interesting problems, I mean, there are a lot of openings in my group for MS research, PhD, postdoc, and basically project associate and those kind of positions. All right. Okay. Thanks a lot.